And with that, I want to start get to the presentation. It's going to be from an organization that I got involved with a few years ago, just listening and learning what they're up to. And I just wanted to really share it with everyone. It's AURI, so Agricultural Utilization Research Institute. And I reached out to them and asked if we could find a speaker. And this guy by the name of Yuka,
Luca
how do you pronounce it?
Zullo.
Zolo
Yeah.
was offered up, and oh my gosh, what a wonderful person to do this. He's got tremendous credentials from here to there. A lot of the information is on our website, but Yuka, please feel free to explain more about yourself, and then we can get into the presentation. So thank you so much for doing this.
Thank you, Doug. And thank you, everyone. And introduce myself. My name is Luca Zullo. As you can figure out from my accent, I'm not from Minnesota, but I've been here for about 30 years. I'm Italian by birth, studied chemical engineering, went to grad school in England, then worked in the oil and gas industry for a few years. And from there, I ended up working on a small move to agricultural commodity processing and ended up working with a little Minnesota company called the Cargill, stayed there several years. And a few years back, I started doing things in my own, started a company, a biotech company with colleagues from the University of Minnesota. It was a great science project. Not so much of a business, but sometimes you have to learn these things. And for the last 3 years, 4 years almost actually, I've been senior director of science technology at URI, the Utilization Research Institute. And URI is a kind of a unique organization, so I will provide you a bit of a overview of what they are. Typical, actually, this presentation that I show you is what we present on a yearly basis to the Minnesota legislature, because URI, so non-for-profit, is actually funded, not completely, but in a substantive amount, about 70% of our funding from the state of Minnesota. And we were created well before my time at the organization, about almost 40 years ago now, by the legislature to help farmers, in the middle of the farming crisis of the 80s, to identify new ways to use their commodity and developing new supply chains for agricultural products. And since then, we are focused on helping from harvest and onwards, and I'll provide you an overview, and then later I'm going to focus on a specific topic that I think is germane to this series of talks, which is anaerobic digestion, which is how we're going to make energy out to organic residues that today often are wasted or going to landfill, created greenhouse gas. And without further ado, I move to the next thing. So what we are, and our mission, organization need to have mission and vision, and we want basically to accelerate the expansion of agricultural economy by empowering expanded use and market for agriculturally derived product. As long as it grows, is harvested in a farm, we can be involved, and can be the main product, can be a co-product, can be a waste product. And our goal is basically we measure our impact by economic impact, and our goal is to deliver $500 million in economic activity for Minnesota by 2026. And I have to say that we are already on target to do that.
Yuka, how long has AURI been around?
We have been around since the early 80s, mid 80s. I think 80. I don't quote me on that because I don't remember exactly, but I think 86 or 87.
Okay.
86.
Okay, thank you.
We have a board of director which represents a lot of you will see a lot of name representing either the legislature, like typically we have the senior members of Agricultural Commission, both in the Senate and the House, and then we have a representative of farmers organization and of agricultural businesses. And as I said, that through the board, not only they provide a fiduciary role to make sure that we use correctly we are entrusted correctly with public funds, but also they create a tremendous link to our rich agricultural environment. We have 34 full and 1 part-time staff. I have to say that the number has just increased by 1. We hired a new person just recently, and we have 2 labs in Marshall and in Waseca, and the administrative office, which is in Crookston, Minnesota, and then we have a client office at the University of Minnesota, which we use mostly for if we have to have meeting in the Twin Cities, but also for relationship with the University of Minnesota, with which we collaborate a lot. The labs are in Marshall and Waseca, are focusing on different activities. In Marshall, we have a meat and food lab. We are particularly good staffed in the meat lab. If you want to start a meat business and you have an idea to test scaling up the production of a new brat recipe, we can help you. We also have a bio-based and renewable energy lab, and also all our analytical lab, and we have a product evaluation sensory lab for new food products. While Waseca is our more industrially oriented lab, and we have densification, the watering, drying, helping to study all these type of processes as they apply to agricultural commodities. We have a food lab focused on food grade commodities, so oil extraction, milling, and we do a lot of work on novel crops like kernza, which is a perennial, an ancient grain that has some tremendous environmental benefits, and there we are working with people trying to do, say, malting of a type of new grain. And finally, we have all the anaerobic digestion activities that are related to really not stopping with the products, but also making sure we minimize waste and reuse the waste. And I will talk about more in detail about those later.
Yuka, can you, you're showing up really small on my screen, your presentation. Is that everybody seeing that? Or is it full size on your computers?
My computer is full size.
I zoomed in for the recording at least, so the recording will be normal. But yeah, for everyone else, it might be a little. There's just black on either side of the screen.
Oh yeah, you know why? Because I have a very big screen. So is this better?
Yeah, I think that would be better, yes.
Yeah, I was going full screen, but I have a very wide screen, and so I think he's trying to squeeze the screen in. So now instead of full size, I will use just the window. So
Okay.
Doug, you can also just grab the screen and make it larger on your own monitor, which is what I did.
I would go back to full screen just for the recording, so it looks nicer, and then everyone just can manually zoom in on their screen.
Yeah,
Okay.
that's what I did.
Okay, good enough. Just wanted to make sure people can see it.
Yeah. Sorry for that. I have too big bar because I have a very broad screen. So what our programs basically we support, we do 3 things. One is commercialization services. This is basically our, if you want, research programs, but it's not only technical research. We help, we have a very strong business development component in the organization. And so we have entrepreneurs that needs help putting together a business plan, and we help with that. Sometimes they don't need technical help. Sometimes they do need technical help. And when they do need technical help, we focus on applied research. But what is unique about URI is that you're going to find a lot of organizations that have very deep technical capabilities, other organizations that have very deep business development capabilities. We are kind of unique in those we merge those two in a single organization. Then, of course, we do public research initiatives that are associated to a topic of clear importance for our ecosystem, where we get either through private or public grants to do more typical research work, but this can be more technical research or could be could be market development research. So an example of two of different of this type of activities, on very different areas. One was being research we did on behalf of corn, and those results now are published in Minnesota Corn website. We did some work on looking at the feasibility of using ethanol as a feedstock to make hydrogen, so corn ethanol. While another example of another public research initiative, we did a research for the Beef Council on optimizing the utilization of co-products of meat processing in small locker rooms. And finally, there is AURI Connects, which is our series of events. We typically have a webinar, and we have at least a couple of big events on a yearly basis, one of which is the Minnesota Renewable Energy Roundtable, which we hold every year in December. And I think, Doug, you probably heard about our last one where we talked about energy efficiency in food processing.
Yeah. Yeah.
As I said, we are in fiscal year 2024, and we go by the farm fiscal year. So our 2025 fiscal year is actually ending in a month, or in June. Yeah, so a month and a half. We had 10 events. We attended by more than 1,000 people, of which 240 were new, 730 from Minnesota, and I would say that the non-Minnesota participation keeps us increasing from 36 states and 4 countries. And then our YouTube, and then we collect about 1,000 views on YouTube after. And as I said, we had, by focus areas, we had 8 in food and 2 in bioindustrial. And for lack of a better term, if you cannot eat it, but still comes from a farm, is bioindustrial. And we estimated that we, based on our work in the period from 2019 to 24, we helped create about 800 jobs, facilitated the more than $250 million in capital investment, $180 million in new sales, and of the capital investment, 85 were completely new. And with a net job creation retaining of 700 jobs. So we do a lot of work with food entrepreneurs. So if you want to start, I'm not going to go in detail reading all these, otherwise it will take too long. But if you want to start a food business, we should be our first stop. We can help you. What it takes to transfer a recipe you do in the kitchen to something that can go in industrial production. What it takes to get a food approved to use in a school lunch, shelf life, nutritional labels, all those things we can help. And we have a lot of collaborations. One thing I would like to stress is AVA, and is our AURI virtual assistant, but is basically an AI-enabled tools where we have distilled all our experience in food, in starting up a food business, and from both a technical and business perspective. So today you don't even need to talk to anyone. If you want to start exploring what it takes to start a food business, you just go online on our website, you go to AVA, and you start interacting with the chatbot, and it says, and it will tell you what it takes, and we can initiate and provide this guidance. And this is an example of some of the food projects we have done. Cannon Bells is a cheesemaker in Cannon Falls. We've been working with them very closely at the inception, and is an example of some of the many companies we have helped. On the bioindustrial side, we work on food, feed, fuel, fertilizer, and as I said, we do technical assistance either on process, but also specific part of the process. You see some example of them. We are the only one in the upper Midwest to have a decorticator, which is the machine that allows, if you get an hemp stalk, to reduce that in usable fibers. And with that, we have done a project with the Minnesota Department of Transportation, where we have contributed to the development of these bio-based hemp mats used for erosion control during road construction. As you know, when you do road construction, often they have to, when there is a ramp or an embankment, they have to put down plastic tarps to avoid erosion until we have vegetation again. That's to avoid, because strong rain could bring erosion. Unfortunately, that plastics then needs to be removed before you plant, and obviously, typically those plastic tarps needs to be landfilled. With this our hemp mat, you just lay the hemp mat, provide the erosion control, and then you just can put a tarp on top, and biodegrade actually is a carbon source and provides a much more environmentally friendly solution using a locally produced product. And then, of course, anaerobic digestion, and we talk about that later, and we do a lot of business development activities. What you see here in this picture is actually a machine that we have where we can basically, is a pelletizer, is a 1 ton per hour pelletizer, and we have all the equipment to basically reproduce a complete industrial process. And you see, in a typical year, we do about 50 projects, so we're pretty busy, and for clients, and 50 projects, of which between a research project and clients project, and yeah, so we are pretty busy. This is another example. This is natural-based fertilizer, where we are blending soy meal with urea to make a more sustainable fertilizer. And here you see the example of the mat I was telling you. This is as the mat is being rolled on the shoulder of a road, and you see how it looks like. Then we have analytical equipment. Last year we made some important acquisition, and so what you see here, a few equipment, including a mass spectrometer, and then some equipment to do determination of biogas potential, which again I will talk about later. But we pretty much can support. We can do a lot. I would say 90% of the analytical work that is required to valorize biomass and so on, we can do it in-house. There are a few exceptions that might require some very specialized equipment, which happens only once in a while, so we cannot justify the purchase, but we have good relationship with people who have those, and so we can provide all the services needed. And as I said, we had a one-time fund last year, so we could actually open up, expand our lab and open up in a new facility, which the Bioindustrial Innovation Center in Waseca, we double our square footage, and that allow us to be way more productive. It says we have some testimonials. I'm not spending a lot of time on those, but I would say that we typically, our clients are very happy to work with us for a variety of reasons. One is also that we provide extremely good value, and for business of a certain type, the state allows to use the state fund to subsidize this work. So I can provide the rates that would be otherwise impossible. So it's a great way for the state to support innovation in this sector. And with this, as I said, events, those are the type of events we do. New Users Forum that we talk about new application, Field of Innovation and Webinar Wednesday are both we are both either a field type of process. So for instance, event, what you saw when that erosion mat being laid down, that was part of a Field of Innovation event where we invite people to come on literally on a field and looking at how these things can be applied. Then Webinar Wednesday, every few Wednesday we have a webinar on a specific topic. And finally, the Renewable Energy Roundtable that I discussed before. And looking forward, again, We are right now focusing on a few areas that are very critical, we believe, for the state. Scaling up food manufacturing. That's by itself, I could talk several hours about that, so I'm not going to go there, but we are certainly looking at what we can do to help entrepreneurs to move in from the first phase where they've proved that a product exists to being able to go to actually scaling up to the market. Food ingredients with a focus on ingredients coming from novel crops. Bioindustrial, I think there is a lot of emphasis in more sustainable production and replacing more products with bio-based products. Co-product valorization, we try to say that everything that is harvested should be used. Nothing should be wasted. So sometimes there is low value streams that come out of a field or form of a process, how we can use them. And that leads into renewable natural gas and anaerobic digestion, which is really a good way to provide a stable and reliable source of energy in rural environments. And I will spend most of my presentation, the rest of the presentation, give you an introduction of the topic and what we are doing there. As I said, I'm not gonna spend more time in those are some of the distribution of our projects. Not surprising, the majority of our projects are in rural area. There are not, but you will see also that we have also quite a few projects in the metro area, because we work with a lot of local entrepreneurs, especially in the food area. So while we are mostly focused on we have a strong focus on the rural environment, we are not just a rural organization. We really focus on the whole of the state. And before I pull up the discussion on anaerobic digestion, any question, I'm happy to answer at this time. Otherwise, without further ado, I'll move to anaerobic digestion.
Yuka, I went down to one of your presentations down in Wasika, I think it is.
Yes.
And you guys were developing new types of machines to harvest new types of products. And now, do you internally build those machines, or do you contract that out to,
No,
people?
we don't necessarily build it. So what you're referring was actually a machine to clean up, I believe, the fiber of hemp. So no, we don't. I mean, we work with the people who eventually will build the machine. So we are not focusing on the building the machine, but certainly we collaborate, or we say, okay, we provide technical specification, we help with the prototyping, and ultimately we also do the testing of the machine. But we are not necessarily involved in the manufacturing. And in fact, what I would like to to stress here is that we focus on a specific area of technology. So we focus using a language that is common in the federal government. We focus on what we call the technology readiness level 4 to 7, which is basically ideas and technology or processes or product that have been already proven at the lab scale and early commercial scale, but need to be scaled up and optimized to be brought to economic fruition.
Oh, okay.
And that also is important because, again, we do not compete with university. We collaborate with University of Minnesota. We have a lot of common interest and common work. But for instance, we don't. But an example is the Forever Green initiative, developing new crops. The University of Minnesota focus on things like genetics, like field trial, and agronomics. And then when they get to a point that we think that there is the yield start getting of commercial interest, we can get involved and we do studies on things like, okay, how you harvest this grain, or better yet, how you clean it up, what is the oil yield, can we make a flour, could this be used as an alternative to wheat to make some product, and so forth.
Thank you.
I have a question. Yuka, my name is Chris Berta. I was wondering, I didn't see you mention in the bioindustrials. I sure wish you would be making a plastic alternative.
Yes, we actually working with people. Obviously, Minnesota is a great leader in that area because polylactic acid was invented here, and we still have nature works as the basis. So yes, we do work in that area, not directly, because as I said, we don't really develop technology in-house. But for instance, an area that we're very active, and again, that itself will be a very interesting conversation. We have been developing, talking about plastic, an alternative to plastics to use for mulching in horticulture. So today you're going to see a lot of, especially if it's not so much Minnesota, although there is some in Minnesota, but California, you're going to see miles and miles of plastic sheeting put on the ground where they produce basically horticultural products. So you're going to see some of those in southern Minnesota, in strawberry fields in the summer and so on. Now, that plastic sheet is actually very important because it actually keeps water in the ground, especially if it's connected with drip irrigation, and also keep pests away. So in a way, minimizes the use of pesticide and minimizes the use of water. But obviously, you have across the United States billions of pounds of plastics that then has to be put, which is not recycled. So we worked actually on an alternative that actually is kind of a paint, looks like a paint. You can spray it, and is actually based on soybean oil, and then it can be blended back in the soil and will biodegrade. And so yes, this whole area of and right now we're working on with a potential investor to see how this can be commercialized. But so this whole area of plastics, alternative plastic replacement is very close to our interest. And
is this a plastic that you could also use to roll the bales of hay that are on the fields? And
not the bale, not those, because require more mechanical resistance. For those, we don't have yet a complete solution, although we think that there is, we look at hemp and some of an hemp fiber as a potential alternative, although we'll have to go to more woven material. And right now we're mostly working in non-woven.
I mentioned it also because, we have exhibits at the Eco Experience at the State Fair, and there's always a University of Minnesota station there where they're talking about the bioplastics, and it never changes. It never goes anywhere. Why? I don't know. But, you go to the boat show, and all these boats are covered. They roll in covered in plastic. That all gets thrown away. Then they get covered in plastic again when they leave. And it all goes in the garbage.
Yeah. Well, yeah, it's a tough problem making. So we can make bioplastic, things like PLA for certain application, but unfortunately, we don't have yet a bioplastics that can actually perform as well as regular plastic for all the application. Or we can make it, like for instance, we can make a bio-based polyethylene from ethanol. That's very doable. But the problem is that then you get polyethylene. Yes, it's renewable in terms of the carbon, is young carbon, but to the end of the day, you have the same end-of-life problem that you have with regular polyethylene. So,
well, good luck on that.
Yeah.
Thank you.
Yuka, any work at all on forest products, or is it strictly?
No, we don't. So forest product, forestry is out of our scope. So obviously, we have another great organization in the state that does work on forestry, and that is NRC in Duluth. And actually, URI was formed at the same time, and basically that is their domain. So yeah, no, we don't focus a lot on forestry. Although occasionally you have seen the pelletizer, we have done work on making wood pellets with people that wanted to blend corn stover with wood pellets and so on. But forestry is not our topic. We really do mostly and the USDA sees, by the way, forestry as farming. So it's not that I says it's not farming, but certainly we look more at the what people conventionally think are farming. Something you plant and you and you
Yeah.
you plant in the spring and you harvest in the fall, and not you know, the 10 or 15-year harvest cycle that the tree farmers have.
Well, it made me think there was a story on TV last night about the forest fires up north, and this insect is killing all the trees and, you know, creating all kinds of, you know, dead wood for the fires. And I don't know. Okay, so somebody else is working on that then.
Oh
Okay.
yeah, they are. And by the way, that has been a big problem even before, because I did before your eye, I did some work on utilization of wood for a bio-based application. And the problem is that the logging industry in Minnesota has declined dramatically. And so right now, at least a few years ago, when I was looking at the data, there were more wood rotting in the forest and decaying for natural causes that was being actually logged, and that's all that caused a tremendous amount of fuel. And now is you know, blights like the one you mentioned are causing even more problems. Ultimately, the problem is that the logging industry has declined because the market, the dynamics of the dimensional lumber industry have led us to have very, very big consolidation. There is only one producer of dimensional lumber that I know left in the States. There is no any longer production of OSB. All are moved to Canada, and so the result is that and because of that, we don't have the loggers. I mean, a lot of logging, which are all family, relatively small business, have gone out of business. And so there is actually nobody, even if we want to manage the forest, even to use the waste wood, that actually go and pick it up. So this is a big problem.
Wow.
Oh.
All right. Thank you.
You're welcome. So I want just to briefly talk about anaerobic, briefly. I'll try to be keeping on the time, but anaerobic digestion. This is a short primer. I'll go to some of the technical discussion. And again, this presentation is available, so I'm gonna be fast on certain area, but I'll try to. Someone never knew want interested in aerobic digestion from a technical perspective. I'll talk more technically today than business, and we'll read from that. But basically, the idea of anaerobic digestion is that there is not such a thing as waste. And if you think about nature, the waste concept is unique to humans, because to our human systems, because there are not such a thing as waste in nature. Everything is naturally recycled. And really what we are trying to do is taking advantage of processes that would otherwise naturally happen in nature. And so we look at things like manure, wastewater biosolids, which is the residual from sewage plant treatment, food waste, and other organics. Other organics can be anything from, well, maybe dedicated energy crops, but could be also organic waste from food processing, waste, like wastewater coming from an oil processing plant or a slaughterhouse. All of these can be alone or together with other material go in aerobic digestion in a digester. And the digester fundamentally produces two streams: biogas, which is a mixture of methane and CO2, and digestate. The digestate is what is left after the bugs have done their magic. And the nice thing about digestate is that it's very rich in residual nutrients, nitrogen, phosphorus, potassium. And so it can be used in a variety of applications. Obviously, it's a mixture of liquid and solids. The liquid is a great fertilizer, is a great water for irrigation, but then can be used for fertilizer, but also for other products. So, for instance, if you go to you buy plants and they're put in those little pots that almost look cardboard, but you see they're not cardboard. And sometimes they tell you can just put this little pot inside the bigger pot and the roots will grow through it. Well, those pots are actually made from digestate coming from a farm where that then has been dried and molded into these little pots. So yes, those things started as probably as a manure, but obviously they don't look like manure any longer, and we explain that why in a minute. And among them, they don't smell like manure anymore. So really, and obviously when the biogas, as I said, is CO2 and methane, and methane is the component of natural gas. So the biogas can be used as is to make electricity. We burn it in a motor, in an engine, and we can generate electricity. Can be put used as a fuel vehicle in a compressed natural gas. Can be used for heating, or after removing the CO2, can be injected in the pipeline, because we can make a product that is virtually indistinguishable from the natural gas you buy from your pipeline. So what is anaerobic digestion? This is the thing. Anaerobic digestion is actually something that wants to happen in nature. We don't have to do anything. It will happen naturally. In fact, is basically what happens when organic matter is decomposed in absence of oxygen. The bacteria, or the consortium of bacteria, will basically digest organic matter and creating gas. And methane and carbon dioxide are the main product of this metabolic activity. And you can actually see example of that. And we have Minnesota is the land of 10,000 lakes. I'm sure that you have been occasionally by a lake and occasionally seen some bubble coming up from the bottom of the lake. That is actually a mixture of gas of methane and CO2, biogas, coming up from the sediment on the bottom of the lake. And you have all the weeds and dead fish and so on, especially if the lake is has a muddy bottom, like a lot of Minnesota lake. You get the sediment of organic material and mud that basically has no oxygen, because the mud seals it out well, and so everything decays. And as decay, forms gas, and as the gas builds up pressure, at a certain point, a bubble will pop up and coming up through the water. What you see to the right, in fact, is an example of something like that. That is more of a bog than a lake, but you're going to see also in a lot of lakes, and it's a very natural process. So the whole idea of what we're doing is really harnessing what is this naturally occurring process, and so that we can actually collect the gas, maximizing the production, the yielding gas, and doing that in a way that then we can have economic value out of it. And this is an example, if you can see the video, of that I
New
want to show
lakes
you.
are rapidly forming across Alaska and northern Canada as global temperatures rise and cause permafrost to melt. Scientists in Alaska noticed something interesting about Alaska's newly formed Big Trail Lake. It was bubbling. Microbes begin eating organic matter that thaws when the permafrost melts and release methane during their digestion. Over a 100-year time period, methane's ability to trap heat is 25 times higher than carbon dioxide. Methane and carbon emissions from melting permafrost are expected to contribute to global warming in the coming years.
And so I wanted to show this video because it points out to two things. One, anywhere we have this organic material that is trapped in conditions where we don't have oxygen, ultimately we will degrade and will liberate this methane. However, the problem with methane, although it's renewable methane, is that it's an extremely powerful climate greenhouse gas. And so if we allow this methane, however coming from a renewable source, methane released in the atmosphere, we will contribute dramatically to climate change. While if we can capture that methane and burn it, now we release CO2, but that CO2 is neutral because it comes from freshly produced organic matter. So as long as we grow, grow more organic material, we harvest new crops and so on, we can say we recycle that carbon, and we produce the energy instead of trapping that methane in the atmosphere. And this is critical because today a lot of those waste material actually go in landfills. And when you go in landfill, you create a tremendous amount of methane that is released. And that's why a lot of landfills will have way to capture this biogas. The problem is that even the best technique, the best landfill in terms of management will only capture between 40 to 50% of the methane produced. And so that is definitely not enough. While if we can do that in a digester, which is engineered, we can capture all of it, and therefore having much better environmental benefit and also being much more effective in reusing that energy as a renewable energy source. So, as I said, we have a long history because, as you said, the biogas, the Assyrian in the 10th century before the Common Era, before Christ, basically, they were known to use biogas. And the observation on swamp gas that I just noticed happened in the 16th century. And in 1776, Alessandro Volta, the scientist that also from which the name, the volt for power charge is related, determined the direct correlation between the amount of organic matter. In 1808, Humphrey Davy, that was a British chemist, figured out that methane is produced by cattle manure. And the first time that someone put an anaerobic digester as an engineering system to capture the energy and to capture the gas was in India in 1859. And today, in India, there is a lot of places where we increasingly small scale, almost family level anaerobic digesters are used to generate cooking gas, which is much better than the alternative because traditionally in India they were using and still do dry cow manure as a fuel, and in a closed environment is a terrible fuel. You don't really want to breathe those fumes. But if we instead put that cattle manure in a digester, now we get clean burning biogas, and it's much healthier. And as I said, sewage gas shortly thereafter was used in Exeter. The first patent was in 1907, and the first time was implemented in a farm was in 1938. At least the time we know on a farm was in England in 1938. So this is not new, but what we have done today is a much better understanding of what it takes to make it happen and integrating better in farm operation and seeing this really as a way to produce a significant amount of energy. So the thing is that while it's a biological process, should not be confused with things like fermentation, say, to alcohol. Fermentation to alcohol is basically almost a single step where you have a single organism, yeast, that takes sugar, so a clear an compound, and as a part of the metabolic process produces ethanol as a product. Digestion is a bit more complex in that we have consortia of bacteria, and literally we have the genome is very complex. I don't think we have a complete understanding of all those bacteria yet. I think there's still a lot of work to be done. And they really look at the material, so a typical bio-based material, which is made up of protein, carbohydrates, fats, and then either lignin or chitin, and they process the material as a whole. And obviously the lignin and the chitin are not digestible, but the rest can be digested. And we have first a step of hydrolysis that provides simple sugar, fatty acid, amino acids, which then we have another set of bacteria of acidogenesis, and then we have another step of acetogenesis, and finally the methanogenesis, the last step, where basically we go through this step. And if we look what happens inside the digester, we can see all these steps by looking at the composition of the products. Now, what makes these complicated when you look at that for an industrial level is that basically, instead of being a single organism that operates, is this large consortia, and these bacteria don't necessarily like the same conditions. So to have a really well operating digester, you need to find the compromise that where everyone is happy, or everyone is not too unhappy. So an example is this. Hydrolysis typically, which is the first breaking down of the material, is really the limiting step, can be the limiting step factor in many times. But sometimes we have very fast hydrolysis, and then what happens, we create fatty acids. So the pH, the acidity of my environment goes down. And guess what? The methanogens do not like that. And so suddenly we stop producing gas, and the whole system crashes. So really the technology of anaerobic digestion is finding optimal condition where we can do this as fast as possible. Obviously happen in nature, but nature is not very fast. We try to accelerate, find the condition we can accelerate to maximize the gas yield and the productivity. Now, as I said, some of these parts are not digested, and what we get this residual sludge, which is not digested, but it's very rich in nutrients, because the majority of the nitrogen, some nitrogen is used, but the majority of the nitrogen, the phosphorus are there, and that becomes a fantastic soil amendment and fertilizer. So, and as I said, it's just basically an engineering system. Looking outside, often it just looks like a big tank, but it's a tank that has to be designed in order to achieve our goals that are based on what type of feedstock are. And really, when you talk about digestion, you're going to hear things like rate of digestion is a high rate, produce gas very fast, or a low rate, it's a bit slower. Typically, it's simpler. How the flow is a stirred tank. Most common is just a big tank mixed. But for instance, you're going to find sometimes a plug flow. Doug, earlier you were mentioning Albershot Farms in Cambridge. They have a plug flow where the material enters from one side and goes through. And basically, you can joke as thinking about the plug flow is like an extension of the cow guts. It's just another big tube. And the operating condition, high temperature, low temperature, thermophilic, they're very high temperature, about under 20 F. They're a bit more difficult to control, but they're very high gas yield, mesophilic, easier to control, low temperature, but low, about 90 F, but a bit easier to control. And then and typically, is a system that you have to maximize gas production, to make it happen fast enough for economic, you need to mix it. And, you will find a lot of different ways to mix it. Sometimes with a mixer, sometimes recirculating with a pump, so hydraulic, sometimes bubbling gas, or a combination. And really, there is not a recipe that works better than another, other than in specific circumstances. Although each person has his own preferences. And then, how much solid, you get a lot of solids, so sometimes you pump something that looks just like water with a lot of dissolved material inside. So again, you're going to hear all these differences, but at the end of the day, the technology is fundamentally the same. Is creating the environment that, given a certain type of feedstock, allows this consortium of bacteria, which exist in nature, they're already there, to adapt themselves to the specific feedstock and maximize the production of gas, and both in terms of quantity of gas, because obviously there is where the economic value is, the more energy you obtain, and also do that as fast as possible, because the faster you are, the smaller is your digester and the cheaper it is. And, as I said, you're going to see a lot of systems. So I have a few pictures there, and, and there are some examples. So to the top here, you're going to see these two are covered lagoons, basically big. They look almost like swimming pool, but then we put on top of that, we put a cover, and you see that the cover looks like a bit of a balloon, and indeed is a balloon. You can actually walk on that cover, and underneath there is gas. You actually use that cover as a hold for gas. The gas then is removed with pipes. But sometimes there can be tanks. Here is another example. That is a more conventional tank with a mixer at the top, all steel, or a combination of the two. This is a very common design in Germany, and we have several also in the US. And what you see here is basically a big tank, but the top of the tank is actually a flexible membrane that inflates as gas is produced. And what you see here is that there is the pipe where you take out the gas, and the gas goes actually in this container where it's treated. In this specific case, actually, the gas, that container, as a electric generator. And so if Europe has been much more forthcoming in the development of this technology, but but we're seeing more and more also in the US, and when you drive by a farm and you see something like that, most likely is a digester where they treat their manure. And as I said, they are not difficult to run, but you need to have some understanding. And so what we do, for instance, work AURI does, is that we work with farmers or other producer organic waste that are interested in say, okay, can we do biogas? And we look at the feedstock characteristics. So what is your feedstock? I mean, they all can produce biogas, but if you give me something that is very rich in starch, or something that is very rich in fats and oil, or something that is as a mixture of all of it with a lot of protein, is going to be, the gas potential will be different, and we'll have to adapt. We'll have to think about differently how to design. Same, you think something that is very liquidy, or there's a big chunk of solid, how much moisture, and we can calculate the biogas potential. And then from that it comes, and then of course the composition is important, because how much carbon you have, how much nitrogen you have, are those in balance? If you have too much nitrogen, you're going to create ammonia, and if too much ammonia will poison the digester and kill the bacteria. On the other hand, not enough nitrogen, it's like not feeding protein to people. Ultimately, you cannot live on a diet of carbohydrate alone, and they will, and also you'll have problem, and the bacteria will suffer. And then from that, you can think about how you operate, how much I have to mix, how I feed it. I could have two different feedstock, and how I mix together, how long they stay in the digester, the organic load, which is how much organic material per cubic feet of digester, what type of temperature operate, can I control the pH? Digester ideally wants to be at a relatively neutral pH, but some type of feedstock, they tend to create a very low pH drop, and that is not good. Then you have to think how I have to adding something to control. And then, auxiliary nutrients. As I said, sometimes if you don't have enough nitrogen, I might need to add a bit of urea or inhibitory substance, and we'll go there. I mean, there's a lot of fear sometimes that, what about antibiotics? If I use antibiotics in farms, can they create problems? And the answer is, it depends. Yes, a lot of antibiotics will kill the bugs. But again, if we can control the amount and we know how much, we can certainly control and avoid that they're a problem. So that is really what we say. And this is really what we're trying to do. You're going to hear a lot of horror story of people saying, oh, the digester did not work, it failed, and so on. Often is because people did not do this work. And this actually sometimes is the misleading nature of anaerobic digestion. It's a process that want to happen, because if you put a bunch of kitchen food waste in a bag, and you seal it and you lift it outside, chances are that within a few days, especially in the summer or spring, certainly not in the middle of a Minnesota winter, that bag will explode. And so digestion wants to happen naturally. So that gives an idea that it's a simple process. And in a way it is. What is not is having reproducible, controllable results. And that's why we try to help the potential users to understand what they're doing here. And that is the type of thing we do. So we can get any feedstock you have, and I can basically do all this analysis and telling how, if, and most probably is yes, you can digest it, but how and how much gas you do, and ultimately if it's something that is economically, you can extract economic value, but also what you can do with what is left. This is an example of the type of experiment we do, which is, looks pretty boring, but in reality is what we do is we go in the lab and we take two feedstock, and over time we, on a very small amount, so I don't need a lot of stuff, we go in a specifically controlled environment, and we let it generate gas, inoculating the system, and we can tell you, how much production of gas over time. And this is the fundamental thing, because then I say, okay, in reality, in real life, I'm not gonna run for 40 days. That is too long. It could be too expensive. You see, at a certain point, after 20 days, more or less, you are in diminishing returns. So I said, okay, I'll design my industrial system around 20 days. And now I know how much methane I can produce. And by this diagram, I can start looking at the other characteristics and starting designing an industrial system. And as I said, I touched a bit of those, but those really what we do is try to help people to understand what they have and how we can process it. And while we have a lot of information on things like manure, dairy manure, we can almost, we don't need to do a lot of experimental work on dairy manure. So well known. Sometimes, we got a question recently, says, well, what if I mix dairy manure with my chicken litter? Well, it's doable, but obviously you complicate is now you're dealing with a new feedstock. And because chicken litter brings, the chicken manure with it, which is has some unique characteristic, a lot of nitrogen, tends to forming a lot of ammonia, so we have to find a way to neutralize that. And also typically, it's not like the manure of cattle that is pretty liquidy, but is actually, is on the litter, which means that there is a lot of wood chips, for instance, how we deal with that. And that's what we're trying to do, really helping the farmers or potential operators to coming up with a strategy that allows them to choose the right technology and understanding how to operate their system. Before I said about temperature, this is a little example, but the temperature range in Celsius. And, again, as a lot of things is so 40 to 55, so say about 120 F, and mesophilic is 30 to 40 C, so about 90 F. You see the difference here? Is that it takes way shorter time working at high temperature than lower temperature. However, the problem of working at high, so in theory, it should cost less, you say, lower temperature, because obviously you think, well, I need a smaller amount of a smaller digester. Well, actually, unfortunately, it's not the case necessarily all the time, because it's much more difficult to control this digester. You see that if the temperature, the activity drops out much faster. And also in Minnesota, winter are cold. So it's way more expensive keeping a digester at 120 when outside in northern Minnesota than at 90. And typically what you do is not only insulation, but also using some of your gas to warm up the digester. And so it was called parasitic load. So ultimately, in a lot of location in our, although it's not necessarily the case for every case, but in a lot of cases, doing mesophilic, lower temperature, although the digester is bigger, might end up being cheaper than with thermophilic, despite the digester is smaller, because now I have a digester that requires more control, more insulation, and has a higher parasitic load in the winter. So though we try to navigate all these trade-offs that often are not obvious, but if you don't navigate them correctly, ultimately you lead the perception that the system doesn't work, because you just have designed a system that is not good for the application. Talk about biogas, as I said, is methane and carbon dioxide, and there is some traces of nitrogen, oxygen. If you do things well, ammonia should be very low. And if ammonia is not very low, you're going to kill the whole digester. So probably then you have another problem. There is water in the gas, but most important, and this is the critical thing, there's hydrogen sulfide. And especially with things coming from gas coming from manure. So ammonia and hydrogen sulfide need to be removed to be used, because otherwise they create corrosion. The technology is pretty easy, but it has to be done. Otherwise, the gas become very corrosive. Carbon dioxide, we remove it only if we are an application like going in a pipeline where you want to make a drop-in replacement of renewable natural gas. But if I want to produce farm energy on the farm, I can use the methane with the carbon dioxide. It works just great without adding that extra cost. Now, as you see, methane is 50–70%. Obviously, the more methane there is, the more energy there is in the gas. And really depends what you have in the feedstock. If you have a lot of carbohydrate, sugars, cellulose, you're going to go on the lower end of this range. If you have a lot of protein, fats, and oil, you are on the higher end. It's all based on how reduced your feedstock is. Either way, you still have a really good amount of energy being produced. As I said, those always need to be managed.
Okay.
Yeah. Doug. One thing, and again, I'm not entering that. One thing that anaerobic digestion does very well is destroying pathogens. So, and this is why it's such a powerful tool for, say, handling things like biosolids and so forth. The majority of bad pathogens like Salmonella, Escherichia coli, and so on are destroyed in digestion. And that means that basically we can, the material that comes out of the digester is a much safer and better fertilizer than the raw manure. And by the way, it doesn't smell. I told you before there is H2S. Well, if you get manure, the mercaptans and sulfur-bearing compounds are what creates the smell, because the sulfur is taken out and then released as the H2S. As long as we capture the H2S and we treat it, which is relatively easy in the gas phase, the digestate is going to be completely smell-free. It's going to have a nice organic smell, not unlike compost. So, as I said, there are a lot of things that can cause this not to work well, and we try to help people to understanding, but ultimately, it's question to design the system and having a good understanding of what your feedstock is, what engineering solution you need, and running it correctly. And you can avoid all these problems. But if you have it, we can help you to sort them out. As I said, when you look what we do, that is what we do. With feedstock characterization needs to be done. We can do bench scale digester, depends. Often we don't have to do that, but we need if we have a common feedstock, or someone wants to try something new, like mixing chicken litter with dairy, or there is something like you have an example, you have something with a lot of starch and can become very difficult to mix. And then finally, we have the ability in our plant, so we can do all this. We can go to a pilot scale digester to 100 gallons. We don't have to do all the time, but if you have you want really strange feed, you want to optimize the carbon to nitrogen ratio and adding or training a new inoculum, or you want to do you're looking at the impact of mixing, or you need to produce say a couple of tons of digestate to do a field trial to see how how it works as a fertilizer. We can do that. And so basically we can help people in this project from starting, say, okay, can I use this feedstock, all the way to come up with a lot of data to design a digester, and we do a techno-economic analysis. And really, we try to be the advocate for the farmers and the owner of the feedstock to make sure that they maximize the value and they can produce something that actually is not only environmentally sound but also economically sound. So I want you a little example, and this is a bit of bit of joking, but give an example of how many you're probably familiar to the F-150 pickup truck and the electric one, and it says, okay, you know, I know you told me that I can do biogas, and biogas can produce electricity. I want to use biogas to, I want to use the poop of my cows to charge my my pickup truck. How many cows do I need? Well, obviously what we would do, we start collecting some manure, and now you see us scrape the barn, and we'll carry out BMP, a biomethane potential, and we can answer this question. So how many cows do I need to recharge an electric Ford F-150? Well, first, a cow typically produce, and I apologize here, I use metric, but basically produce about 7 kilograms, plus minus 5 kilograms per cow per day. This is like a lactating cow. If it's not a lactating or is an heifer, it's about half, but 7 kilos, or give or take 12 pounds of manure per day. And this is total solid. That is on a dry or on a dry basis. Now, of these total solids, only some actually is biologically available, the volatile solids, because obviously the cow, there is stuff, there are minerals in it that are not biologically available, and other components. So basically, and we call those volatile solids, and there is analytics we do to determine both TS and VS. And on average for dairy cow is 0.56 kilograms, so say around 11 pounds, give or take, of per cow per day. Now we say that we can destroy on a typical, doing a BMP experiment, we see, oh, we can convert about 38% of those volatile solids in methane in the time that makes sense, you know, in about 2 weeks. And the yield is, we produce about 0.76 cubic meter of methane per kilogram of volatile solids. And that is actually, let me, that is, well, I cannot do the by memory, the conversion, but I will give you that in a second. Is volume in cubic meters, in cubic feet. That is 26 cubic feet of methane per cow. And so basically I convert that in, I convert that per cow, sorry, per kilogram of volatile solids, which means that I produce 1.6 cubic meter of methane per cow. And as I said, I put an efficiency factor. I says I produce maybe you know, the methane is not, the industrial digester is not as efficient as my little laboratory setup. So 1.60 cubic meters of methane, which is, I'll tell you in cubic feet in a second, volume and cubic feet, so cubic meter, cubic feet is 55 cubic feet of methane per day. Now, the energy content of methane is 35.85 megajoule per cubic meter. By the way, is a million BTU for 1,000 cubic feet, but so 38.5 megajoule per cubic meter. I can put that in an engine, 35% efficiency, and that basically means that I produce 5.57 kilowatt hour per day per cow. And this is actually, to remember, close to 5.5 kilowatt hour per day per cow. That's how much electricity can we produce out of a dairy farm. Consider that we have dairy farms now in the US that they have thousands of dairy cows. And you see that now suddenly you can tell why some of these projects can produce megawatt of power. Well, the battery pack of F-150 Lightning is 131 kilowatt hour. And so that means that I need 24 cows to have a charge a day of my Ford F-150 Lightning. And well, 24 cows is not that many. The average dairy farm in the US is about 300.
Yeah.
But it's going up. So you see that it can actually, so if you think you're a farmer, you can say, well, probably I can produce as much electricity as I need to run my farm and having more to spare, to sell.
I love Lois's comment, cow power equals horsepower.
So as you see, we say, well, yeah, unfortunately, we have not been very good in putting, and despite the current climate, I'm a big fan of electric vehicles. And I'm saddened by the fact that we have not been as effective in building an infrastructure, but I says, well, you can start, this can start. So, if you want, a farmer can produce their own electricity from their cows and still running the electric pickup truck. So I want just to go about, what about a bigger farm? A 2,000 dairy cows can produce in a day enough gas to warm 7 Minnesota homes in January. And, we are big in January, we are big gas user because we like to keep ours warm, or enough gas to provide a truck with equivalent of almost 900 gallons of diesel. And so while this number, when you think the consumption of, say, of fuel across the United States don't look big, when you think about at the farm level, you see that you can be a big contributor to making farming a community much more sustainable. So with this, again, there is so much more to say, but I will, as I said, any question? I probably spoke in too long, but I hope that provides some insight on what we're trying to do with helping farmers to maximizing the use of their agricultural waste.
Chris, go ahead.
Well, I have a question about cost. This is, first of all, this is just amazing, and I can't imagine the background you have in order to figure all this all out, and I hope that the federal government hasn't cut science education, for a career like yours. But I was wondering, you're years and years and years ago, I remember working with a farmer, learning about his process. I forgot the name of the farm in St. Cloud area. And he wanted to build this digester, and he did kind of on his own, and using it to fertilize his fields and produce wind power and warm the barns. And Xcel Energy, it took him 25 years to pull it off because Xcel Energy would not approve it and would not buy it until finally they said yes. What kind of pushback do you find from that question, and also the cost to a farmer to basically assess, analyze their product to see what their possibility might be?
So let me say, so the cost to a farmer is actually to analyze this case and so on is relatively low. Right now, there is enough interest that a lot of developers want to do this, and we provide very subsidized services, fundamentally because if a farmer comes to me, we can provide really inexpensive services because we are the state of Minnesota. The fund we get to the state of Minnesota fundamentally is to provide a subsidy to the work we do for the farmers. So, if a farmer comes and asks to do this type of consulting, would be $200 an hour plus laboratory fees and so on. And I have my lab people work for, if a farmer comes, that we work for about $20, for less than $20 an hour, because we can provide that, because the rest is subsidized by the state. So the cost is, and often we have other grants through USDA and so on that virtually we can provide free services. So that is certainly reduced. The problem of electricity, you point out a big problem. I think right now we don't have good policies to do distributed electricity. I think it's going to be a major problem, and we need to have better policies because I think there's so much opportunities, but the utilities typically are kind of reluctant to have the system plugged into the grid. We can do it, but sometimes it takes time. And I wish those regulatory barriers would come down. As far as the cost of the digester per se, they're not inexpensive. They can cost a few $100,000 to some case. Some you go to Riverview, they probably have $20 million invested. However, they actually are a good economic investment for a variety of reasons. Not only you have energy return on investment, but also it becomes a manure management system. So for instance, if you go to Riverview, you go in the farm and they have 10,000 dairy cattle and you can't smell anything because they have a fantastically well-run digester. That means less complaints from the neighbors, means that you can add more cow and making easier permit. Now you also get a better product of the digestate that can be composted and can be better applied. We are very limited on direct application of manure because some of the characteristics of manure. And I cannot store. If I store, it smells. And people don't like having big manure storage nearby. But digestate is different. It's like compost. It's easier to apply, can be applied over a broad period of time. And nobody's going to complain to have those because they don't smell. So the result, we have a lot of beneficial things that can pay. The challenge has always been this: the farmers are busy, and unless they're a big industrial farm, they don't have the bandwidth to run even a digester. A digester are not that difficult to run, but if you are a farmer, you are already busy doing farming stuff, and so even the relatively small additional maintenance work on a digester, unless you are someone like Mr. Aubenschild in Cambridge, who is kind of a passionate thinker, becomes complicated. And so then the question for us, what we're working now with our organization, is ensuring that there is technical support to help them and to make sure that things are done correctly and to maximize and to provide them that type of support that is needed. And we hope that by building more infrastructure, then we can create actually the support infrastructure around it. A bit like, if you buy, now a lot of farmers, they still tinker, but if they really have work to do on their tractor, they're going to go to the implement shop and there is an implement shop in every county or two, because again, there is a lot of tractors to do maintenance, and we hope eventually we go in that direction. But certainly government incentives and policies are very important, but those is something that also makes agriculture more environmentally friendly. So I think we still see, obviously we have seen a bit of reduction of some incentives, but ultimately less than I feared. They're still there. And so we're still optimistic that this will happen. And of course, in the state of Minnesota, we see this as a critical way to reduce, electricity. We have still the goal of being carbon-free in our electricity production by 2035. There is a lot of work can be done in this area. And we are actually developing now a roadmap that we plan to unveil at the end of the year to present to the state how to maximize gas production. In theory, if just looking at what theoretically is available, we could replace 100% of the natural gas consumption in the state electricity consumption.
Wow. Yuka, is Haubenschild, are they still powering Caterpillar generators with their biogas?
I haven't talked with them in a while, but I think so. And
okay.
It's a very simple application. You just need to put a scrubber to remove the sulfur, because otherwise you can corrode the engine.
Yep.
But otherwise, then the gas goes straight in and works like a charm.
Yeah, I know the XL at one point used generators at the landfill, and that was the problem. The emissions that came out of it were quite dangerous, and so they backed off at that time. I don't know if they're still doing it or not, but
well, it's very common now. What happens is that there is a unique characteristics of landfill gas with this siloxane. We don't have siloxane with this type of waste, and siloxane can create some pretty nasty emission. Again, but so actually H2S, because we'll increase SOx emissions. They're all manageable, but you need really to understand your gas and do the appropriate cleanup. As I said, it's all doable, but we have seen people not says, "Oh, I don't need to do the gas cleanup," and then more than anything else, we start seeing engine failing because there's a lot of corrosion.
Yep.
Because the sulfur with moisture reacts, forms sulfuric acid, and boom, then you get a lot of corrosion, and your engine, after not even a year, the valves on the engine look like Swiss cheese.
Did you ever meet Rich Hillskamp?
No, I don't remember to have met him.
Yeah, he was at the Haupenschild trying to pull off, I don't know if it was hydrogen or whatever, but another gas off of that system. And
I saw the Haupenschild system, and they had a biofilter, which works very well and is a well understood technology now for removing sulfur. And it's particularly useful, the biofilter, to remove sulfur for in biogas, because the co-product is actually sulfur cake. And that is actually fantastic. You can just take it and land apply, and the crop needs sulfur, so you can recycle that sulfur in a very beneficial way to your crops.
I'm sorry to stop this. We have to break for our board director meeting, but I got one final tough question for you.
Yeah.
Which are better producers, Holstein cows or Herefords or Black Angus?
Well, we'll not enter that. That is a question of religion. And I have colleagues and friends that are involved with either one, so I don't want to, and I'm not a farmer, so I said, okay, I'm not gonna enter in that discussion. I don't want to lose any friend.
Yeah, everybody always pictures the Holsteins because they're so attractive.
Exactly. That's the typical is the Holstein that is always the one is always is traditional dairy cow. But actually, in Minnesota, Jersey are more numerous.
Yeah. Any final questions? One more, if somebody has one. If not, we'll
I just have to say, I can't believe it. You guys mentioned it. Hobenchild Farm is the one that I visited and toured with a group of kids. We were doing exhibits for the Science Museum about it, and we all had to put on our little slippers and walk through, so wear our masks so we didn't contaminate it. I can't believe it. They are still. It sounds like they're really doing great guns.
Yes, they are.
Well, thank you so much. Fantastic presentation.
You're very welcome.
So impressed with what the organization's doing, and your knowledge on this end of it was just fantastic. And I love the idea you came up with of powering a Ford Lightning. So that was great. So thank you again, and I'll be in touch with you. Okay.
Thank you. I appreciate that. Thank you.
Yeah. Thanks so much.
Goodbye.
Thank you.